Is substitution still a method that we can use to solve a system of equations if one of our equations is not already solved for a variable? So when we look at these two equations, neither one of them has an isolated variable, like there's not an x equals or a y equals in either one of these equations, but could we still use substitution to solve them? And the answer is not only yes, but substitution actually should be our preferred method here. Because if we look at our first equation, x plus 2y equals 6, while it's true that we do not have an isolated variable, it's a very simple matter to get an isolated variable. We can solve this equation for x very easily just by using the subtraction property of equality and subtracting 2y on both sides. So this would give us x equals negative 2y plus 6, or 6 minus 2y if you like. And now we do have an isolated variable. So it's important to have an isolated variable in a substitution problem because now in our second equation we can replace our x's with negative 2y plus 6. So when we look at that second equation, 3x minus 4y equals 28, the x right here can now be replaced with negative 2y plus 6. And the only thing we have to keep in mind when we do that substitution is that the thing that we substitute, needs to go in parentheses so that the 3 is being multiplied by both the negative 2y and the plus 6. So as long as we use parentheses, we are good to go here. So before we start solving the problem, let's check and make sure that our substitution has accomplished the intended purpose, which is, are we now solving an equation that only has one variable in it? And the answer is yes. This new equation that we've written only has a y variable, which means we can eventually solve it to where we know the numerical value of y. So let's go ahead and do our distributive property. 3 times negative 2y is negative 6y. And 3 times 6 is a positive 18. We'll leave the rest alone for now. So there's what it looks like after the distributive property. We've got a couple of like terms that we can combine. We can combine the negative 6y and the negative 4y together. Negative 6 minus 4 is negative 10. So we've got negative 10y plus 18 equals 28. We don't have any more like terms to combine, but we're just 2 steps away from having the value of y. So let's go ahead and subtract 18 on both sides using our subtraction property of equality. So we'll have negative 10y on the left and a positive 10 on the right. And then the last thing we'll do is divide both sides by negative 10 using our division property of equality. And 10 divided by negative 10, of course, is negative 1. And there's our value of y. So the value of y is negative 1. Great. We're halfway there. The solution to a system of equations is a coordinate pair. So we have the y, we now also need the x. But luckily we've got right here an equation that will tell us what x is when we substitute our y. So let's take that equation and replace the y with negative 1, which is what we just discovered. We just discovered that y has a value of negative 1, so let's do a second substitution. And so now it's just some arithmetic. Negative 2 times negative 1 is a positive 2. And 2 plus 6 is 8. So the value of x is 8. So after doing all of this work, we have learned that the coordinate pair that is the solution to this system of equations is 8, negative 1. So just because we have an equation that doesn't have an isolated variable just given to us, doesn't mean substitution isn't an option. Here, substitution was not only an option, it was the best option. This was certainly less work than graphing would have been. So solving one for x and then doing substitution was the quickest, easiest way to get the solution.